Dear students, in today's lecture we are going to study mechanical force acting on unit area of a charged conductor. Now consider a charged conductor of any shape on which charges are uniformly distributed, and this charged conductor is placed in a medium of permittivity epsilon, which is equal to epsilon 0 K. Now consider a small area ds of this charged conductor, and let sigma is the surface charge density on this area ds, and hence charge on area ds is again q is equal to sigma into ds. Let point A, which is outside this charged conductor and near it, and point B, which is inside and near to this charged conductor. Then consider E1 is the electric field intensity due to charges on area ds, and E2 is the electric field intensity due to charge on remaining part of conductor. At point A, the electric intensity is directed, so resultant electric intensity is directed outwards, and the electric intensity due to charges on area ds is directed opposite to each other. Outside the conductor it is outwards, and inside the conductor it is inwards. So E1 due to charge on area ds directed opposite to each other, outwards outside and inwards inside the charged conductor, and the electric field intensity due to charges on remaining part of the conductor, which is E2, and this electric intensity is directed outwards in outside the charged conductor as well as inside the charged conductor. That means E1 due to charge ds is directed opposite to each other inside and outside, and E2 due to charge on the remaining part of the charged conductor will be directed outwards. Again, we know that the electric field intensity at a point outside the charged conductor is given by sigma is equal E is equal to sigma divided by epsilon 0 K. At point A, the electric intensity, total electric intensity E is equal to E1 plus E2, and which is equal to sigma divided by epsilon 0 K. So this is equation number 2. as we know that the electric field intensity inside the charged conductor is 0, because inside the charged conductor electric intensity due to charge on this area ds is directed towards the left side, and the electric field intensity due to charges on remaining part of the conductor is directed outwards. Both are opposite to each other, and therefore E inside the charged conductor, which is equal to 0, and therefore we write mod of E1 minus E2 is equal to 0, or from this we write E1 is equal to E2. Say this is equation number 3. So E inside the charged conductor is 0, and hence E1 is equal to E2. Then substitute this value of equation number 3 in equation number 2. Then we get E is equal to E1 plus E2, that means E2 plus E2, which is equal to sigma divided by epsilon 0 k, or we write 2 times E2 is equal to sigma divided by epsilon 0 k, and finally we write E2, electric intensity due to charges on remaining part of the charged conductor is equal to sigma divided by epsilon 0 k. Say this is equation number 4. So the value of E1 and E2 is equal to sigma divided by 2 epsilon 0 k. So E2 is equal to sigma divided by 2 epsilon 0 k. Now the area ds is in the electric field which is produced by the charges on this remaining part of the charged conductor. That means ds is in the electric field of E2. As the charge on area ds is positive, and also the charges present on the remaining part of the conductor are also positive, then force will act on this area ds. To explain this, suppose that the area ds is for short time taken from this charged conductor, and here is the remaining part of the conductor on which charges are also positive, and therefore there is a force of repulsion between these two, and hence this area ds exerts a force, and due to that force this area ds is pushed outwards, and this force due to which area ds is pushed outwards due to remaining charges on the conductor is called as mechanical force, and this mechanical force is given by the force on area ds is equal to charge on area ds multiplied by electric field intensity E2, and this expression is obtained from the definition of electric field intensity. electric field intensity is nothing but force acting on unit positive charge. By using this concept, we write the force on area ds is equal to charge on area ds multiplied by electric intensity. And hence we write this force is equal to charge on area ds, and the charge on area ds is sigma into ds multiplied by value of E2 is equal to sigma divided by 2 epsilon 0 k. Therefore, the mechanical force acting on area ds is given by sigma square ds divided by 2 epsilon 0 k. This is equation number 5. So this is the mechanical force which acts on the area ds, due to which the area ds is pushed in the outward direction by the charges present on remaining part of the conductor. And we want to find the mechanical force per unit area, which is small f is equal to mechanical force divided by area ds. So mechanical force per unit area, small f is equal to capital F divided by ds. That means mechanical force upon area, which is equal to, if we divide this equation number 5 by ds, we get sigma square divided by 2 epsilon 0 k. Say this is equation number 6. And this equation number 6 gives the mechanical force acting on unit area of a charged conductor. And in this expression, in the numerator, there is a term sigma, and as we know that sigma is equal to charge per unit area, and if the charge is positive, then the square of this is sigma is also positive. Charge is positive, then sigma square is also positive. If charge is negative, again sigma square is also positive. So this mechanical force per unit area of a charged conductor is F is always directed outwards. So mechanical force per unit area is always acting in outward direction, and this mechanical force per unit area is also called as mechanical stress, or it is also called as electrical pressure. Also it is known as outward pull per unit area. Outward pull per unit area. So mechanical force per unit area of a charged conductor is given by the formula small f is equal to sigma square divided by 2 epsilon 0 k. Then this expression can also be written in terms of dielectric constant K and in terms of electric field intensity. So we know that the electric field intensity E is equal to sigma divided by epsilon 0 k. and therefore this sigma is equal to epsilon 0 K into E. As the mechanical force per unit area is given by the formula small f is equal to sigma square divided by 2 epsilon 0 K. Now in this expression substitute the value of sigma, we get small f is equal to epsilon 0 square K square E square divided by denominator as usual 2 epsilon 0 K. And in this we cancel out 1 epsilon 0 with this epsilon 0. We cancel 1k with this 1k, and the final expression comes out to be 1 by 2 epsilon 0 K E square. So this is the another form of mechanical force per unit area of a charged conductor, which is 1 by 2 epsilon 0 K into E square, and in this formula the term 1 by 2 epsilon 0 into K is constant, therefore mechanical force per unit area of a charged conductor is directly proportional to E square. So F is directly proportional to E square. So in this article we have derived the two formulas, one in terms of surface charge density and one in the form of electric intensity and dielectric constant. So mechanical force per unit area of a charged conductor can be given by two formulae. Small f is equal to capital F divided by ds, which is equal to sigma square divided by 2 epsilon 0 K, and another formula is small f is equal to capital F divided by ds is equal to 1 by 2 epsilon 0 K E square. And by using this formula we are going to study the next article, which is called as energy density of a medium. As we have already discussed that a mechanical force will act on area ds due to charges on remaining part of the conductor, because charge on area ds is positive, charge on remaining part of the conductor is also positive, there is a force of repulsion, and due to this area ds is pushed outwards through small distance. Now suppose that again this is the charged conductor of any shape situated in a medium of permittivity epsilon equal to epsilon 0 K, and due to the mechanical force acting on area ds, this area ds is displaced through a small distance dx from its original position, and in order to bring this area ds again to its original position on the surface of the charged conductor, we have to do work, and we know that work done to bring area ds through small distance dx on the charged surface, dw is equal to F, that is mechanical force, multiplied by distance dx. So work is equal to force multiplied by distance. And again we know the value of mechanical force acting on area ds is 1 by 2 epsilon 0 Ke square into dx and multiplied by the displacement of the area ds, which is equal to, in this expression, the term ds into dx. So this ds multiplied by dx is nothing but the volume swept by the conductor. And when we bring this area ds, which is pushed outwards to its original position, the work is done, and that work is stored in the medium in the form of electrostatic energy. And therefore, the work is stored in the form of energy which is equal to du, which is equal to half epsilon 0 Ke square into ds into dx is the volume swept, that is dV. So the energy in a medium is given by this equation, and hence energy per unit volume is called as energy density of the medium. So dW divided by dV is called as energy density of the medium, and which comes out to be 1 by 2 epsilon 0 Ke square. So the force acting on unit area of a charged conductor and the expression for energy density are same values, which is equal to half epsilon 0 Ke square. Now finally we will discuss two situations. One situation is this mechanical force per unit area of a charged conductor is same for all shapes of the conductor. So mechanical force per unit area is same for any shape of charged conductor. This is the question, and answer for this question is no. The force per unit area is not same for any shape of the charged conductor, because if the conductor is arbitrary, that means the shape of the conductor which having so many point parts, and we know that the charges near the pointed charge are closely distributed and charges on the curved parts are widely distributed, and hence mechanical force per unit area is not same for any shape of the conductor which is charged. And finally, again one question, or we say that numerical or MCQ. Suppose that a coin is charged in air. So initially a coin is charged in air, and now this coin is placed in kerosene. Then number one, charge. Number two, charge density. Number three, electric field. Number four, energy density. Number 5, mechanical force. So out of these 5 quantities, which quantity is affected? So initially the coin is placed in the air, and after that the same coin is placed in the kerosene. That means dielectric medium is changed. And when dielectric medium is changed, out of these 5 quantities, the charge on the coil remains same. Then charge density will also remain same, because density, surface charge density sigma is equal to Q by A. As charge is same, therefore surface charge density is same. But electric field intensity, the electric field intensity is given by E divided sigma divided by epsilon 0 K. As this K changes, the electric field also changes. Similarly, energy density, the formula is U is equal to 1 by 2 epsilon 0 K square. Again here the term is K. Therefore energy density also changes. And again the mechanical force per unit area, the formula is small f is equal to 1 by 2 epsilon 0 K square. Again here the term is K. Therefore in this situation, the charge and charge density will not be affected, but the electric field, energy density and mechanical force per unit area are affected. So in my next lecture, we will take some numericals which are based on these 2 articles, that is mechanical force per unit area on charged conductor and energy density of the medium. In this problem, K is given, which is equal to 8, and energy density is provided. That means du by dV is provided, which is 26.55 into 10 to the power 6 joule per meter cube. And we have to find the electric field intensity is equal to how much. So in this case, again we have to use the formula. Energy density is equal to 1 by 2 epsilon 0 Ke square. And therefore E square is equal to 2 into U divided by epsilon 0 K. If we substitute the values, 2 into U is 26.55 into 10 to the power 6 divided by epsilon 0 8.85 into 10 to the power minus 12 into K is again 8, which is equal to 3 into 10 to the power 6 divided by 4 into 10 to the power minus 12, and which is equal to 3 by 4 into 10 to the power 18. And therefore E is equal to square root of 3 by 4 into 10 to the power 18, which is equal to square root of 3 into 10 to the power 9 divided by 2. And finally the value of root 3 is 1.732 divided by 2 into 10 to the power 9, and which is equal to 8.66 into 10 to the power 8, and unit is volt per meter or Newton per coulomb. So in this case, radius of circular metal plate is given small r, which is equal to 10 centimeter, 10 into 10 to the power minus 2 meter, which is equal to 10 to the power minus 1 meter. Again, a charge is given q, which is equal to 20 microcoulomb, equal to 20 into 10 to the power minus 6 coulomb, and we have to calculate the outward pull, and the outward pull is equal to capital F, and the formula for outward pull is F is equal to sigma square into ds divided by 2 epsilon 0 k. But here we have provided a circular metal plate. So the circular metal plate has two sides, and therefore it has area equal to 2 times ds, and therefore our formula becomes F is equal to sigma square, again sigma is equal to q by a, therefore F is equal to q square divided by ds into 2 times epsilon 0 k. Now if we substitute the values, q square 20 into 10 to the power minus 6 bracket square divided by ds, ds is nothing but ds is equal to pi r square, and which is equal to 2 into 3.14 into radius is 10 to the power minus 1, its square, which is 10 to the power minus 2, again multiplied by 8.85 into 10 to the power minus 12, and the value of k is 1. And therefore, again here this 2 multiplied by 2. And if we solve this, we get the outward pull, capital F, which is equal to 3.598 into 10 to the power 2, and unit is Newton. In this problem we have provided length of the cube, which is 5 centimeter, 5 into 10 to the power minus 2 meter. Again intensity is provided 200 volt per meter, which is 2 into 10 to the power 2 volt per meter, and K is given, which is equal to 8, and we have to find the energy contained, that means du or U, which is equal to what? And here we have to use the formula energy density per unit volume, which is du by dV, but we have to calculate du, so du is equal to 1 by 2 epsilon 0 k E square into dV. Now if we substitute the values, 1 by 2 into 8.85 into 8 into E square, 2 into 10 to the power 2, that means 4 into 10 to the power 4 into dV, that means volume, the length is 5 into 10 to the power 2, its cube, which is equal to 5 into 10 to the power minus 2 its cube. So which is equal to
power 8.85
into 10 to the power minus 12. So which is equal to 1 by 2 into 8.85 into 8 into 4 into 125 and into 10 to the power this minus 12 plus 4 minus 8 and minus 6, which is equal to minus 14, and this comes out to be 16 into 8.85 into 125 into 10 to the power minus 14, and which is equal to 17.7 into 10 to the power minus 11 joule.